Hello, everybody. We're starting section 2.1, and here it is, 2.1, operations with matrices. So first, I just want to say, determining whether two matrices are equal, that's very straightforward. Adding and subtracting matrices is very straightforward. Multiplying a matrix by a scalar, very straightforward. And when we get to multiplying two matrices, that's where it's not as straightforward, but we're going to explain all that. So let's just start. So when are two matrices equal? Well, first of all, we learned what a matrix was. We learned that previously. And basically, two matrices are equal. By the way, we use, generally speaking, we use capital letters, to represent a matrix. So, and sometimes if you look at number 2 here, sometimes we use this notation. And this just represents a collection of numbers A sub I sub j. And number 3 is what the A sub I sub j will look like. It's just different ways of representing a matrix. Anyway, how do we add two matrices? When are two matrices equal? So two matrices are equal only if they're the exact same size and they have the exact same entries in the exact same positions. So for example, if you look at the example number 1, matrix B and matrix C look kind of equal because they're both 1, 3, but they're not, because one is, as you can see, is a vertical, one is horizontal. The vertical one, by the way, is a 2 by 1 matrix, and the horizontal one is a 1 by 2 matrix. Now, matrix A and matrix D could be equal if X is equal to 3. In fact, that's a nice way to do because really this is a that's what it means. Because if X is equal to 3, then both these matrices are 1, 2, 3, 4. They're both 2 by 2 matrices. Everything works out. It's all good. It's all good. Sometimes, again, I'm just going through a lot of things quickly. So, by the way, we have a matrix which is just one column, like such as matrix B. We call that sometimes we call it a column matrix, or sometimes we call it a column vector. Now, the word vector, I'm sure you've heard that word before, and we're going to get into vectors a lot, but not yet. That's coming up. In matrix C, as you can see, it is just one row, and that's it. So we call that a row matrix. Sometimes we call it a row vector. Same thing, no problem. Sometimes we'll sort of partition a matrix. Look at this. So matrix A is 1, 2, 3, 4, and I could sort of partition it into 2 separate columns, and I could write it A1 then little line in A2. A1 represents the column matrix of 1, 3, and A2 represents the column matrix of 2, 4. This is, again, just different notation that we're going to use, and I want you to get a little familiar and comfortable with that notation. Now, basically, when we add matrices or subtract, same thing, we can only add two matrices if they are the exact same size, and we add them entry by entry. So for example, here's the definition of matrix addition. Now, this is this definition is written in a very fancy way, but all it means is that you add up each individual thing. So let's look at example A. Let's look at example A. So we have the matrix negative 1, 2, 0, 1, and then we have the matrix 1, 3, negative 1, 2. So when we add the two matrices, we add in the upper left, we add the negative 1 in the upper left and the positive 1 in the upper left of the second matrix. Then we add the two upper right numbers, 2 plus 3. Then we add the two lower left numbers, 0 plus negative 1, and so on and so forth, and we get 0, 5, negative 1, 3. Again, very straightforward. All we're doing is just adding the entries by entries. And matrix B, problem B. So if you notice, the second matrix here is full of zeros. You may have noticed that, and we call that wait for it, a zero matrix. Because if you have a matrix which is all full of just zeros, that's called a zero matrix. And notice that when I add the zero matrix onto another matrix, I just get the same old matrix. So just like 0 is the identity element of addition with regular plain old numbers. Zero matrix is the identity element of addition for matrix, for matrix. Now see, same thing. Let's look at D. Example D, it's undefined. You know why? Because the first matrix is a 2 by 3, the second matrix is a 2 by 2, and I can't add a 2 by 3 and a 2 by 2. The only time you can add two matrices is if they are exact same size and just as we said before. Just that's why I first started it with equality of matrices. Okay. By the way, if the first matrix was a 2 by 3 and the second matrix is a 3 by 2, that's also, you can't add them because they have to be exact. They have to have the same size. And by size, I mean this many rows by that many columns. Now, sometimes when we work with matrices, real numbers refer to scalars. And so first of all, why do we use them? Why do we have to make up another fancy word that you never heard of before? Scalar. The reason is because it sort of scales the matrix, means it makes it uniformly bigger or smaller, depending on what you're multiplying by, or negative or whatever. I'm just saying. So basically, when we multiply a matrix times a scalar, all that means is that we're putting a scalar on the outside of the matrix, and that scalar is multiplying every entry inside the matrix, kind of similar to the way if you put a number outside of a parenthesis, it distributes into everything inside the parenthesis. So look at example A. I'm sorry. Look at matrix A. I'm sorry. Matrix A, here's an example of scalar multiplication. Matrix A is, as you see, 1, 2, 4, negative 3, 0, negative 1, so on and so forth. So if you look at example A, small a, it says 3A. I'm sorry, I keep on saying the word A. Sorry about that. But 3 times capital A, I stick the 3 on the outside of the matrix. And then, as you can see, I multiply everything inside the matrix by 3. And now, so the top row, which used to be 1, 2, 4, now became 3, 6, 12. The second row of in example A, which used to be negative 3, 0, negative 1, is now negative 9, 0, negative 3. Now negative B, let's look at the second example. Negative B, well, that's just negative 1 times everything that's in B. So the top row, 2, 0, 0, is now becomes negative 2, 0, 0. And by the way, when I'm reading matrices, I keep on reading it row. Like for example, matrix A way up on top, matrix A on top. When I read it for this recording, and I say 1, 2, 4, negative 3, 0, negative 1. That's not necessarily a right way or a wrong way. It's just the way that I'm doing it, just to be a little consistent. If you want to read it vertically, 1, negative 3, 2, 2, 0, 1. I'm talking about matrix A up on top. There's no right or wrong. I'm just doing it for that's just how I'm rolling. That's what kids say now, right? That's how I roll. So now if I want to do the operation of 3A minus 2B, so basically I take matrix A, multiply it by 3, take matrix B, multiply it by negative 1, and now add those two matrices, or subtract, whichever way we want to say. Subtracting and adding is kind of the same thing. Subtracting is just adding the negative, whatever. Anyway, so I get my final result, as you can see, way on the on the end of example C is 1, 6, 12, negative 10, 4, negative 6, and 0, 7, 0, 4 on the bottom. And that is matrix addition and subtraction. Now, matrix multiplication is like, it's not like it's one thing if you multiply two parentheses, you know how to distribute it. It's kind of, matrix multiplication is a little, has to be defined. And it has to be defined in a way that's kind of useful. So I'm going to show you a reason why it might be considered useful, and then we're going to go from there. So here we have a story. We're going to tell you a story. And this is a story of hot dogs, soda, and peanuts. So it looks like someone's going to a stadium. Oh, it says a football stadium. And so in this football stadium, there are different items sold, peanuts, hot dogs, and sodas, and they sell them in the south stand, the north stand, and the west stand already. So these are the so we have, if you look here, we have two matrices. The matrix on the left, which is a 3x3 matrix, and that shows you how many of each item was sold at each location within the stadium. The second matrix is a 3x1 matrix, meaning 3 rows, 1 column, and that's talking about the price per item. So that means that that a bag of peanuts, I assume they give it in a bag, costs $2. A hot dog costs $3, and a soda costs $2.75. I'm getting hungry doing this example. Sorry. Anyway, but I digress. So let's say you want to know how much money was made. So let's say we want to figure out the total sales of these items. You know, peanuts, hot dogs, and sodas are the top sellers apparently, and we want to figure out how much money was made. Let's say at the south stand. So look at the sort of little equation on the bottom. I have 120 peanuts times $2 a peanut. I have 250. I'm reading the bottom now. 250 hot dogs times $3 a hot dog, and 305 sodas times $2.75 a soda. And if you multiply that out and add that all up, you're going to get $1,828.75. Let's not forget the 75 cents. So, and similarly, I could figure out how much money was made in the north stand and the south and the west stand, doing the same process. So this is an example, believe it or not, of matrix multiplication, because we could write because when we multiply two matrices, as we're going to see, you kind of multiply the rows of the first matrix times the columns of the second matrix. And if you now what happened here, again, I'm taking these same numbers. You wind up with a 3x3 matrix. That 3x3 matrix is the, I just got rid of all the words, but it's the same numbers, 120 whatever, the hot dogs and the peanuts and whatever. And the second matrix that's being multiplying is the prices, and then the third matrix, which on the other side, on the right side of the equal sign, which starts with 1828, that matrix is the total amount, total amount sold, you know, in dollars. So this is a way of multiply. This example kind of typifies how we multiply two matrices, believe it or not. So let's get to the definition. Now here's the definition of matrix multiplication, and when you look at this, you're gonna go, huh? Like what? So I want to show you just how it kind of works, and then the definition will make a lot more sense. So let's say we have a matrix A and a matrix B. Now, one thing you're going to see right away when you multiply two matrices is that the only way it's ever going to work is if the number of columns in the first matrix, and when I say first, I'm talking about going from left to right. The only way it's ever going to work is if the number of columns in the first matrix is equal to the number of rows in the second matrix. That's the only way it's going to work, and you'll see why that is. So what we do is that we multiply these two matrices. We're going to get a new matrix, 311, C11, C12, C21, C22, dot dot, and that's now. Let's see what. Let's just go through it. I don't want to complicate things. We'll go through it, and we'll understand a lot as we go through it. So the first thing I'm going to do is I'm taking, if you notice, you see how it's highlighted in pink. I'm taking the top row, the first row of the first matrix, times the first column of the second matrix. But when I say times column, I'm kind of doing it. The first number is -1 in that row, and then the first number in the column is -3, and then the second number in that top row is +3, and the second number in that column on the second matrix is -4. And I'm multiplying the -1 times the -3 and the +3 times the -4, multiply, add it up, and we get -9. This is exactly what I did really with the hot dogs and the peanuts and the whole thing. By the way, this product, if anyone's familiar with this, there's something you may have heard of, something called a dot product. If you don't know what that is, we are going to get to that in this course. But some of you may have seen dot products if you took like Calc 3 or something, we multiply sort of like dot, and we're actually going to do here 6 separate dot products. And again, if you don't know what a dot product is, don't worry about it. If you do know what it is, then that's what we're doing here. We're kind of doing 6 separate dot products. So now we got the first entry, C11. Well, let's look at the next one too. So to get C12, now C12 is the first row, second column of the product, the final product. Now that means I'm taking, since it's the first row, second column, I want to take the first row of the first matrix and the column of the second matrix, and that's how I'm going to get C12. So it's going to be -1 times 2 plus 3 times 1, which if you crunch that out, you get 1. Notice that if I want to get the entry that's in the ith row and the jth column of the final product, I take the ith row of the first matrix and the jth column of the second matrix. That's the way this works, and it's good to remember that. So the ith row of the first matrix and the jth column of the second matrix produces the entry, the ith row, jth column of the final product. Same process, all these, I'm not going to go, and we get all the different numbers here, and the final product of the 2 matrices is 1, 4, 6, -15, 10, and again, this is that same process, and this is how we multiply 2 matrices. So as I said before, in order to do this, now what's always going to happen, and again, this is something, what's always going to happen, in order to multiply a matrix A times a matrix B, notice, you see, look at the bottom here. I want to make this a little bigger here. It's always, so A has to be, let's say, an n by n matrix, and B is an n by p matrix. So the n's, if you notice, have to be equal. Which is what I kind of said before in words, that the number of columns of the first matrix has to equal the number of rows in the second matrix. And if and you'll see it just doesn't quite match up if that doesn't happen. Just try multiplying 2 matrices, you'll see right away why that is. And the outer numbers, A was an M like Mike by N, and B was a N like November by P. So the outer numbers wind up being the outer numbers of the product. So the inner numbers have to match, and the outer numbers wind up being the size of the final matrix. And that's just the way this works. That is the way this works. So let's so now, if sometimes let's go back to example 4. Now, if I would try in example 4, we just did the product AB. What if I would try to get the product BA? Well, if I did the product BA, I'd be stuck, because the number of columns in matrix B is 2. The number of rows in matrix A is 3. So if I try to multiply BA, it ain't even going to work. So not only is matrix multiplication not necessarily commutative, sometimes it's not even defined. I mean, there are times, let's say, for example, if A and B were both 2 by 2 matrices, then I could do AB and I could do BA. It is possible. If A was a 5 by 7 and B was a 7 by 5, I could do AB and I could do BA. But actually, if I multiply a 5 by 7 times a 7 by 5, I'm going to wind up with a 5 by 5. If I switch it around and do the 7 by 5, multiply that by the 5 by 7, I want to put a 7 by 7. So you could see that very often matrix multiplication is not even possible to be commutative, because sometimes one direction is defined, the other direction is not defined. Sometimes one is going to give you a 5x5 matrix, one's going to give you a 7x7 matrix. You know, there's many reasons. It is possible sometimes when you have two square matrices that are the same size, it is possible that you can multiply them, the AB and BA will wind up being the same thing. But very, you know, it's actually less common, believe it or not. It's more common that AB and BA do not equal the same thing. That's just the way it is. Okay, what is the general? So this is the general pattern now for matrix multiplication, which is that, again, in this example I'm showing you right now, I took the ith row of the first matrix, and then I took the jth column of the second matrix, and I kind of did that dot producty thing, where if you look on the bottom in red, it says AI1 times B1J, AI2 times B2J, plus AI3 times B3J, and so on and so forth. And all that work, all those numbers that I'm crunching, finally gives me the one number, Cij, which is the entry in the ith row, jth column of my product matrix. And that is how matrix multiplication works in general. And again, here's just some examples just for you to see. So notice in example A, I took a 2x3 and multiplied that by a 3x3, and my final result was a 2x3 because the inner numbers matched and the outer numbers become the size of the new matrix. In example A, I could not have switched this. I could not have switched the order because the ones have matched. Example B, I have now example B is kind of interesting because if you notice that I wind up getting I have matrix A times matrix B, and I get the final answer. Now, if you notice, the final answer is actually the same as the original matrix A. So that's kind of interesting. And we're going to learn that this matrix, if you look at matrix B, I don't want to give too much away, but if you look at matrix B, notice it's just ones down the diagonal, and then has everything else is zeros. That's actually going to be what's called the identity matrix of multiplication. If you have a matrix, if you take any 2x2 matrix and multiply it by 1, 0, 0, 1, the way we have in this problem, you're always going to get the same matrix. And if you have a 3x3 matrix or 4 by, we'll see. We'll get into this this identity matrix, but not the second. Example C. So I have this guy right here. I take a 2x2 times a 2x2, and whoa, look at that! I wind up getting. Now look at my final answer. My final answer is that 1, 0, 0, 1. You know, that matrix, which I said before was the identity matrix, now became the product of these two matrices in example C. Well, guess what? That means, again, we're going to get into this, but I'm just telling you right now as a little sneak preview. That means that the two matrices in example C are multiplicative inverses of each other, because that's what a multiplicative inverse is. You multiply it, you get the identity element. Now this is really interesting. Example D, I'm multiplying a 1x3 times a 3x1, and really it's like one nice, it winds up being one simple dot product, and I get a 1x1 matrix, just like I said I would. Now if I take these same two matrices and I multiply them in reverse order, so now I have a 3x1, 1x3, and my final answer is actually going to wind up being a 3x3 matrix. And that's just, again, if you go through the whole matrix thing, that's how it works. So that's kind of like awesome. I take the same two matrices, I do it one way, I get this tiny little one, I get this tiny little just one, and the other way I get this big 3x3 matrix. So that's kind of like kind of awesome. So as we said, in general, matrix multiplication is not commutative. It is usually not true that AB is equal to BA, but we're going to get into that. We're going to get into that later. Okay. Of your equations, very practical application. Now, if you think about it, if you look at a linear equation, remember x1, x2, x3, that's like x, y, z. So if you look at a typical linear equation, well, really, this entire equation could be rewritten as follows. I could write it, if I look at the coefficient matrix, that's all the A's. And if I look at a column matrix of the three variables, X, Y, Z, and then I look at a column matrix of the three constants, B1, B2, B3, really, this equation can be written as AX equal B. Because if you think about it, look at the bottom, on the bottom here, look at the matrix A, which is a 3 by 3. Look at that matrix, a column matrix, which we're calling. Notice that, by the way, it's a bold X. So bold X indicates that it's a matrix, not you know. And if you think about it, these two things are saying the exact same thing. The three equations on top, and these two, then this matrix product on the bottom, they're saying the exact same thing. Because the only way, because the first column of my product matrix of my answer is A11 times X1 plus A12 times X2 plus A13 times X3, and that's going to equal the top number, which is in this case B1. That's exactly what the top equation is saying. So this is like awesome that I'm taking an entire equation and I'm expressing it in such a compact form, which is kind of cool. So if I have a matrix equation, AX equals 0. So A is this, A is 1, negative 2, 1. X is the column of the, and 0. By the way, notice bold, the bold 0. So that means the 0 matrix, not the number 0. AX equals 0. We're talking about the 0 matrix, which is this vertical 0, 0 matrix. So again, I'm taking a 2 by 3, multiplying that by a 3 by 1, and my answer is going to be a 2 by 1. Well, these matrices here really represents these two equations down here. See what we're saying here? These matrices here, if I multiply matrix A times matrix X, and I get the 0 matrix, that's the same as these two guys right here, these two equations down here. And then we can solve these two equations. For now, we're going to learn more fancy ways of how to solve linear equations. But for now, we're going to take this and we're going to just solve it like we normally do. I'm not going to go through the whole thing, yada yada yada. And I'm getting my final matrix. I'm putting the solution in matrix form. My final matrix is going to be X1, X2. It's going to be T, 4T, 7T, and we're going to have T times 147. So this is something we did already, just not in matrix terminology. We did it. We would have said it's T, X equals T, Y equals 4T, Z equals 7T. We did a whole bunch of problems like this already in the previous chapter. I'm just right now putting it all in matrixy form, if that makes any sense. And if you look at it on the bottom here, depending on what T is equal to, like for example, if T equals 1, I get this first matrix 147. If T equals 2, I get 2, 8, 14. If T equals 0, I get 0, 0, 0. Equals negative 1, I could constantly put in infinite, different values of T, and keep on getting new column matrices, which are solutions to this equation. So this is an equation which has infinite solutions, but that's not shocking because, as you know, there were 3 variables and 2 equations, so it's not shocking that there are more. Sometimes we represent matrices in a different way. So I have the system AX equals B. So sometimes it's more convenient to, now this is, so if I multiply A times X, so my top number is going to be, the entry on top is going to be A11 X1 plus A12 X2 ... plus A1n Xn, and we kind of get that whole dot product thing. That's going to be up on top. And I'm just going to leave it as a big thing. Now, even though the top of this bottom matrix, even though it's the whole thing, this plus this plus this, that's just one entry, because those are just numbers which I'm going to multiply and add and get it down to one final number. And the second entry in that column is also just one number. and down the line. So even though this looks like a big wide matrix, it's actually a thin column matrix. It's actually just a thin, simple column matrix with an n by 1 column matrix. So, but now this big fat matrix is equal to adding up these little skinny matrices. Now, what I'm doing here is I'm treating, this is easier to understand if you look at it backwards. If I would start with what I have on the bottom, the equation on the bottom, if I would look at a column of let's look at the first column, the first skinny matrix on the bottom, A11, A21, dot, 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 AM1. And if I multiply that by a scalar, so I'm treating this variable now like it's a scalar, I get a new matrix, which is A11, X1 plus A21, X2, dot, 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 dot. So if I would take these bottom guys and multiply them out and add them up, I would get what we have up this big fat matrix on top. So this is called writing matrices in a partition way. And now I could say, well, this column, my first column of A's, I'm going to use that notation. That's the A column. So AX, I'm now expressing it like this. AX is equal to X1, A1, where A1 is now a whole column matrix, and X2, A2, and dot, 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 all that equals B. So this is this is just another way of expressing it. Now, what we have here is, this is a word we're going to be seeing a lot, but just linear combination, or actually it's 2 words. What we have here, we've expressed this matrix product as a linear combination of the column matrices, and the column matrices are A1, that's column A1 represents column 1, A2 represents column 2, and so forth. And it's a linear combination of the columns with the coefficients x1 and x's. So there you go. This is a linear combination. This is just a definition summarizing what we just done. And alrighty. So if you have a system of linear equations, a way of viewing that is that I could take this system of linear equations, I could say I could express it as x1 times the column 147, x2 times the column 258, x3 times the column 369, and that equals, and if I put all that together, I'm going to get the column 036. So again, I could do my whole Gaussian elimination like we did in chapter 1, and I finally get x1 is equal to 1, x2 is equal to 2, x3 is equal to -1. And again, x1, x2, x3, that's what we often call, we used to call xyz, and I'll still sometimes call it xyz. And it's kind of cool because we're viewing this now as taking 3 matrices and combining them to get this 4th matrix. It's really very different. The geometry of it is very, very different. It's a very different way of viewing this geometrically. And we can partition matrix in all these different ways. We can partition matrices by columns, by all kinds of fancy ways. And when would we partition a matrix in which way? That really depends on the problem that we're working on and the situation we're working on. But that is the story. There are many real life applications. That's nice. And that is the end of 2.1. It's been a great thrill. And the next time we meet will be on 2.2. But I have to do something recording.